Today we're going to start talking about our final topic, which is going to be data centers, virtualization, and cloud computing. So this is going to be sort of a nice follow-up to some of the distributed systems stuff we talked about. So first we're going to talk about what is a data center. It's probably a term many of you have heard at some point, but we'll talk about what a typical data center actually entails. And then we'll talk about virtualization, which is a important sort of OS technology you should be aware of, but it's also a particular use in data centers, and we'll talk about how that's done. And then we'll talk about cloud computing, which is sort of a very general term, but refers very much to the use of data centers and virtualization, and we'll talk about how all of these terms are kind of tied together. So let's start by talking about what is a data center. Right, so a data center is basically a big giant warehouse of computing resources. Right, so a typical picture of a data center is this big, huge building which has huge numbers of servers, CPU cores, disk arrays, right? Just lots of computing resources all packed into the same location. And data centers are used by typically big companies to run very, very large distributed applications, right? So a company like Google, which is running a whole wide variety of products, right? Obviously Google Search is their sort of most high profile, right? But they are servicing thousands or tens of thousands of users all at the same time, right? Constantly. So they have massive computing resource needs, and so the way they handle those needs is by running their applications in data centers. So Google owns a bunch of data centers that are distributed all over the world, and each of those data centers can have tens of thousands or hundreds of thousands of machines in them, right? So huge amounts of processing power all located together, and pretty much all the big tech names, all the big tech companies, like Google and Facebook, Apple, Microsoft, right? All these big companies extensively use data centers to run their massively distributed applications. So examples of concrete applications that are run in data centers, right? Google Search is obviously one. Amazon, for example, is another big example. Amazon is a big player in data centers. So Amazon runs their online shopping store and a wide variety of other things in data centers. Something like Netflix, right? Netflix is a very common user-facing application. That's another example of something that's run out of a data center, right? So when you go to Netflix.com and you're streaming video, that video is being streamed to you from some data center located somewhere, right? In among tens of thousands of other machines. Right, so lots of different examples. So now let's take a look at what is a data center actually inside? What does a data center look like? Right, so this picture here shows an actual interior of a data center. Right, so you can envision this basically, as I said, a giant warehouse of servers. Right, so it's sort of the picture is sort of take something like Costco and replace all of the merchandise with servers stacked on shelves. And that's kind of your picture of a data center, right? You've got aisles and you've got these huge racks, and all of the racks are just filled with computing equipment, right? So you have your racks of actual servers that are performing computation, right? You have storage arrays, you have infrastructure to support networking, network switches, right? Because you have all these tens of thousands of servers, they're obviously all networked together, right? So you obviously have infrastructure there. And then there's a lot of related infrastructure that's needed to basically just keep all of this stuff running, right? So you can put all these servers together, but then there's a lot of related stuff that you sort of need in the physical environment, right? So for example, right, cooling is a big issue when you have all of these many servers together, right? I mean, when you go and buy, a desktop computer, right, your computer typically comes with, maybe a couple of fans for cooling, and that's pretty much it. But things are a little bit more complicated when you have racks of thousands of machines all jammed into a very tight space, right? That generates a very significant amount of heat. And so in order to handle all of that heat, cooling infrastructure is actually a significant component of a typical data center. Also, in order to just in order to provide all the power necessary to run all this equipment, right, that's substantial as well. both for something like cooling equipment, right? If you are running a bunch of air conditioning units to cool your data center, right, that's going to use a lot of electricity. And then, of course, the computing equipment itself will also use a lot of power, right? And then you'll need things like backup generators, right? Because when we're running these massive distributed applications, right, reliability is also another thing that is really of high importance. So in order to provide that, right, we need things like backup generators in case in case the main power connection to the grid goes down. So, as I said, data centers are located all over the world. Actually, we also have a data center that's fairly local here. There's a data center that's located down in Holyoke that was actually built in conjunction with UMass called the Massachusetts Green High Performing Computing Center. And so that shows that that's an actual picture of the data center down in Holyoke. This is not a particularly large one, but it is still, you can see that's still a fairly sizable building. And so, these just shows a couple of pictures of the interior of the data center, right? So, for example, down here on the left and on the right, those are basically cooling pipes that are basically pumping air in order to cool the equipment inside the data center. This is a picture of, these are actually some of the machine racks, right, that are actually filled up with servers. Now, one interesting question to ask is, well, what actually determines where we set up our data centers? Like, why would we actually set up a data center, in Holyoke? So, based on what I've said, what might make somewhere a good site for a data center? Yeah. Cheap real estate. Yeah, that's a really good one, right? Because if you want to build these huge buildings, right, and as I said, this is a fairly small one, but really big data centers can be the size of multiple football fields, right? So really, really big buildings. So cheap real estate's one important consideration. What else? Yeah. Cheap electricity. Yeah, that's the other big one, right? Because we're using all of this, we'll see in a little bit, I'll show some graphs, but essentially, the actual cost of the power is a major consideration in the total cost of actually running the data center. And Holyoke actually has very, very cheap power, in large part due to the fact that there are hydro facilities down there generating power off the river. Right, so Holyoke actually has very cheap power, which is another reason why it's been a good site for building a data center. Right, because let's say you might have a typical server that takes maybe a kilowatt of electricity, then scale that up to a couple of thousand servers, and I think the MGH PCC uses something like 10 megawatts of power. But that's, again, fairly small. Very large data centers may use as much electricity as, maybe even a small city. The G in that stands for green, right? And that obviously refers to essentially the energy efficiency of the facility, right? So obviously, if your facility is using a ton of electricity, then obviously using less electricity is a significant, that's a significant benefit if you can achieve that. So for example, one of the ways that the data center in Holyoke is comparatively green is that oftentimes, in order to cool the servers, rather than running a ton of air conditioners, it actually just pumps in air from outside, right? Because if outside air is cooler than air inside the data center, then you can essentially cool your machine just by pumping in air from the outside rather than running air conditioners, right? And so that's actually what a lot of these pipes are doing. They're basically just pumping in a ton of air. Right, and so the data center is also green in the sense that it's using power from green sources, right? It's using hydropower, right, which is very clean. So that's another way. Yeah. No, there are air conditioner. There are chiller units as well, which use a lot of power, but they're there but left idle whenever possible, right? So obviously, if it's a really hot day in the summer, and the exterior air is very hot, then obviously you will potentially run those air conditioners. But whenever possible, we can leave them off. Obviously, around here, the climate is relatively cool most of the time, so we can leave those off a lot of the time. Yeah. So also just to give you a sense of the importance of power usage in all this, as a general rule in a data center type environment, for every dollar you spend on electricity to actually run the servers, which is significant, right? Because servers, when you have tons of them, use a lot of power. You're typically spending another dollar on energy just to cool the servers, right? So power is very important, and also a significant subcomponent of that is just power spent cooling the servers. Now, but all this is still very expensive. The MGH PCC costs about $80 million to build, right? And that's essentially just for the infrastructure. That's not for the actual servers in it. So right now, the data center, I think it's, this may be a little outdated, but I think it's something like 40% full, meaning that 40% of its machine capacity is actually taken up by servers. And that's obviously constantly growing as machines are deployed. But just the actual infrastructure of the data center is very, very expensive. So one essentially alternate approach to actually go about building these data centers is essentially a modular approach. So the idea here is that rather than going and sort of upfront designing and constructing this really massive, expensive warehouse building, you can basically just get these modular containers that are basically off-the-shelf building blocks for a data center. Right, so the idea is that you get maybe one of these, shipping containers that's maybe 40 feet across, and it essentially comes to you stocked with servers and sort of all of the other equipment built in, and all you basically need to do is take that and plug it in to provide electricity, and obviously, hook it up to a network and so forth, and then that basically gives you an easy way to sort of build up a data center out of these, modular components. Right, so that is an easier way to sort of scale up your data center. Right, if you want to add more machines, you can just go out and buy more of these modules, rather than if you are building a huge warehouse and your warehouse fills up. Right, there's not sort of an easy way to extend that once you've reached your maximum capacity. Right, but as we just saw, even for a relatively modest data center, it's still very intensive and expensive to build one of these data centers. So, that sort of gives us a little introduction of what a data center actually is. Now let's talk a little bit about what some of the technology is that actually goes into, some of the software technology that actually goes into building data centers. So, one of the main techniques that's used in data centers is called virtualization. And this is not just applicable to data centers, but it's very much used there. So, essentially at a high level, virtualization just means we are going to take some machine interface and use it to mimic the behavior of some other system, right? Some other interface, right? And so one easy example of this is essentially providing some other operating system on top of some underlying operating system, right? Because one of the ways we've talked about operating systems is essentially providing some interface for programs, right? You're running an operating system and it's providing an interface, and programs written to run on your operating system are using that interface. So virtualization is where we're basically going to mimic another interface on top of the same underlying hardware. So this was actually introduced quite a while back by IBM in the 1970s, and it was introduced because of the issue that back then mainframes were the big thing, right? So when people bought machines, they bought these $1-million mainframe computers. And computing equipment, the hardware was changing very frequently, right? So every so often a new mainframe would come out and it would have a more advanced architecture. It might support new operations. And the problem there was that in general then you would not have backwards compatibility with all the software you had running on your old mainframe, right? So you'd get new features, the hardware would support more things, but all of your old software written to run on it would not actually work anymore, right? You'd have to go and essentially port all of your software to run on your new system, right? And that's not very good when you are spending all of this money on new hardware and then you're having to redo all of your software, right? So IBM came up with this idea of virtualization to say basically we can give you the new hardware and then we're basically going to give you this virtualization layer that's going to essentially simulate the behavior of the old system, right? And then you can run all of your same software on the new system just through that simulation layer, and that simulation layer is basically going to make it look to your application like it's actually running on the old type of hardware, right? Regardless of what the actual underlying hardware is, right? So, as some simple example, maybe we have here on the right, we have, maybe some type of CPU, CPU A, and that has some interface that programs can use, right? Interface A. And then, we go out and buy some new system that has some new CPU with different features, right, CPU B, right? And so then we're just going to add this layer, on top of interface B, right? The simulation layer obviously has to know how to use the new hardware. But that simulation layer is then going to present the same interface A on which we can run all of the same programs, right? And then we don't need to modify